Okay, so we have seen that different block floating point format might have a different block size. So in this video, what we want to see is we want to study the effect of different block size. So in this example, I considered MXEP4 number format. So the top chart basically shows MXEP4 number format, which has a block size of 32. In the bottom chart, we created a hypothetical MXEP4 number format where I reduced the block size to 16. So therefore, you have two blocks. You have the first block, 16 numbers, and the second blocks, right? So on the top chart, you have 32 numbers. Now, out of this, we also added an outlier. So this outlier is marked in green, green color, right? And as you can see that as I plot all these numbers, the original numbers in BF16 were in blue color. And then once they get quantized into MX format, they snapped into one of these orange square, okay? So what I'll do is that I will slowly change the value of this outlier and we'll see the impact on the quantization, right? Now, when I do that, you will see that this outlier slowly moves up, and then after some point, I start to show an arrow. It's because the outlier values falls beyond zero point 0.8. So I'm plotting here minus zero point 0.8 to zero point 0.8 because I want to show you the impact of the quantization specifically within this range, because then it will be very clear. So when the outlier, the green blob, goes outside of this range, then it will show an arrow. But if you actually want to see the value of the outliers, that's shown here, right? The second thing to notice is the scales. The scales for the whole block here, there is one scale. For example, in this example, when the outlier is 0.88, I have only one scale for the top chart or the top MXFP4 format. For the bottom, since you have two different blocks, I have two different scales. For the block A, left side, you have a scale factor of 1, and the block B, you have a scale factor of 0.5, right? So let's start with a very small outlier, and you can see that there is literally no difference between the top chart and the bottom chart. And you can see the outliers are 0.33. The scales for the whole block is 0.5, and in the bottom scales for the left and the right block both are 0.5. As we start increasing the value of the outlier to some values, for example, here my value is 0.53. You can see that in the bottom chart, your scale factor for each of the blocks are different now, right? So if I keep increasing this, you will see the effect is more prominent. So for example, around here of outlier value of 1.48, the left side has a scale factor of 2, on the right side has a scale factor of 0.5. And what's the impact here is that the quantization error is very high in the top chart when you have a larger block of block size of 32, right? But in the bottom, there is no effect on the second block on the right side. So we often use the word called blast radius. So basically, when you have outliers, so when you're using a block floating point format, you'd expect there is some probability of outlier falling in that block. As you reduce the block size, for example, in here, what you are doing is if you have, let's say in this case, one outlier in a block, you are reducing the effect of the outliers within that block, right? So the blast radius for block size of 16 is only 16, whereas the blast radius for block size of 32 is 32, right? So by reducing the block size, you are basically improving the quantization quite a lot. And if you have multiple outliers, you might have a slightly different effect. But as a big theme, that assuming that you have equal proportion of outliers in your block, then smaller the block size is better in terms of quality. So let's run through this, and if I increase the outlier values to 2.67, for example, here you can literally see that these values are getting corrupted more and more but here the block B is quite good. And if I go to something like 6.47, you can see this block, most of the values are 0, whereas in here, in the bottom chart, the block A is doing pretty bad, whereas block B is pretty good. So if you calculate the overall mean square error, you'll see the block size 16 is doing relatively better, right? And you have to do this for the whole tensor, for example, a whole model, and you have many, many blocks, so your effect will be, different. Let's look at if I reduce the block size to further granularity to block of 18. So now in this case, what we should see is that the radius, the blocks radius has been reduced to only 8 numbers, right? So your second block, third block, and fourth block, you will see no effect, right? So I haven't changed the example, it's the same numbers. Only thing I change is the number of blocks here, right? So in the top chart, I have block of 32, the old chart, and the bottom I have a block size of 8. So let's look at the animation. As you can see, only this block is impacted. All the other 3 blocks are not impacted. Now, what is the kind of effect here? Should we keep going for smaller block? Well, it depends on the trade-off, right? There's a hardware penalty to pay. Smaller the block, you have to have more partial sums when you're doing dot product. So your cost will be more. So there's a trade-off. You have to really go and figure out what block size, what should be the minimum block size for your problem or workload or model, and for hardware, what's efficient. So just to finalize on this chart, that you can see in the bottom, when you have a block size of 8, I have 4 blocks, I have 4 different scale factor. Okay, let's look at something slightly more interesting, where I put in 2 different outliers now, right? So let's look at here. So I have a outlier here, which is 0.53, and I have another outliers, which is 0.9, right? So in the block of 16, basically these 2 outliers, the impact of individual outliers are different for each of the block. So block A scale is decided by the green outlier, and the block B, the scale is decided by the red outlier. But in the top, when the block size is 32, what you will see is that as I keep increasing the A outlier value, the green outlier value, eventually the role of the who is the outlier will change, right? So as a result, at some point, the scale will change, but the effect of the scale will be dependent on which is the highest outlier here, right? So for example, here, if I keep changing the value, as you can see, nothing happens, but around here, when I am changing the outlier A value slightly higher than the outlier B, then you start to see there are more effect on the top, and you see that effect here on the left side of the block, that is the block A, has some change, but the right side, you don't have any change because your scale is decided by that block's outlier, which is the outlier B, right? So if I keep doing that, you will see the effect more prominently. As you can see now, you only your block A is impacted here, whereas block B is untouched, right? And this is an important point, that when in real scenario, you don't only have one outlier, you will have multiple outliers. And depending on how close the outliers are, your effect of quantization would be different. But at the end of the day, if your block size is smaller, then this outlier switching effect also would be much less to this kind of switching, right, of scale values. So let's look at the full block once with the full animation. You can see outlier A grows up, and then this block is affected at some point, and top everything is affected. And if you calculate the mean square error, you will again see that block of 32 has more effect than, and the effect in the bottom chart is much lower. Now here, the second block, the outlier was always fixed. But what if I have a situation where the outlier actually swap, and then you have a very different effect, which you often see in real scenario. So let's first look at the animation here. So I have a block size of 16 and block of 32, and I have two outliers, green, and red. And you can see that the scale setter, so there's a new row here which says scale setter. So here scale setter for a small value is outlier A, but when I keep increasing the outlier, you will see the scale setter will change. And so let's look at the animation first, and then you will see the difference. Right? So you can see that here at some point, outlier A was setting the scale, but when I go here, outlier B is setting the scale, right? And this is an interesting case, right? So if I come somewhere in the middle, for example, here the role are switched, so outlier B now sets the scale. So in the top chart, you see a very interesting effect. So if I keep increasing this in the top chart, at some point you will see that outlier B will set the scale. Um, but interesting enough that in the top chart, the scales don't change at all, right? Your total quantization error or mean square error is same, right? Whereas in the bottom, you see that the quantization error from left block and the right block are different, right? So initially, you have more quantization error in the block A on the left block. But as I cross this particular threshold, I have less quantization in the left block, but I have more quantization in the right block, right? And this is happening because the role of the outlier is changing. So over time, which one is the outlier is very different, and as a result, you have a different effect. Now, this happens quite a lot if you have, very big full tensor, depending on which one is like, if you have, many outliers, which one is going to dominate? It depends on where you are splitting the block, right? So smaller the block, again, the theory is very simple. Smaller the block, your blast radius is smaller. Higher the block size, your blast radius is bigger, so the effect is more prominent, right? So there you go. So this is where we kind of studied the effect of block size, and as a bottom line, you want to reduce the block size according to your workload of the model. But at the end, you also have to do the trade-off analysis with what's the impact on the hardware.